Welcome back to the Deep Dive. It is February 15th, 2026. If you're listening to this, chances are you've spent the last, 5 or 6 years hearing a very specific obituary being read over and over again.
Ah.
The obituary of the internal combustion engine.
Oh, absolutely. It was the dominant narrative, wasn't it? The EV or bust era. Every headline, every conference.
Exactly. We were told that by 2025, pistons would be relics you'd find in a museum. We were told batteries would solve everything from scooters to supertankers.
Yeah.
But here we are, mid-February 2026, and if you look at the heavy-duty sector, the engine hasn't died. It hasn't even retired.
Yeah.
It's gone to the gym, it's cut out the carbs, meaning the carbon, and it's running on something else entirely.
It's running on hydrogen. And I think more importantly, it has graduated from being a science project, a sort of retrofit experiment, to a strategic industrial pillar.
So today, we're doing something a little bit different. We are shifting gears. We aren't just commentators today. We're going to role play. For the next hour or so, I want you to imagine that we are senior technical strategy consultants at a top-tier global engineering firm.
Okay. I like it.
And you, our listener, you are the board of directors for a major automotive engineering client. You've hired us to give you the unvarnished truth about this technology.
And because we're approaching this as consultants, as you said, we need a proper framework. We can't just throw ideas around. We're going to use a classic McKinsey-style approach. We call it MEC.
MEC.
Mutually exclusive, collectively exhaustive.
That sounds like some serious corporate speak for we're going to cover everything without repeating ourselves.
That's essentially it, yes. It means we break the problem down into distinct, non-overlapping pillars. So for today, that's the market economics, the combustion physics, the emissions reality, the material science challenges, and then finally, the geopolitical landscape.
Okay, so a full picture.
A full picture. And by using this framework, we can answer one very specific, very important strategic question for you, the board. Is the hydrogen internal combustion engine, the H2ICE, is it just a bridge technology that's going to vanish in 5 years, or is it a permanent destination?
And that really is the multi-billion-dollar question, isn't it? Because if it's a bridge, we shouldn't invest too heavily. We should just, patch up our old diesel lines and wait for fuel cells to get cheaper or better.
Exactly.
But if it's a destination, well, then we need to retool the whole factory. It changes everything. So, consultant, let's start at the top. Give us the executive summary. What is our core thesis for the board today?
The thesis is simple and it's direct. H2ICE has graduated. Between, say, 2021 and 2023, we were in what I'd call the retrofit phase.
Right.
We were taking old diesel engines, drilling some holes in the manifold, feeding in some hydrogen, and frankly, hoping they didn't backfire. That era is over. In 2026, H2ICE is a dedicated, optimized technology. It is not a placeholder for fuel cells. For the heavy-duty and off-highway sectors, and this is the key phrase where heavy meets dirty, it is the superior long-term solution.
Where heavy meets dirty. I want to put a pin in that, because that sounds like a critical part of this strategy. We're definitely going to break that down. But first, let's talk money. As a board director, I'm looking at the bottom line. My engineers and my strategists have historically argued against the engine based on efficiency.
Right.
A hydrogen fuel cell vehicle, an FCEV, is technically more efficient at converting a kilogram of hydrogen into motion than an engine is. So why would I choose to burn fuel in an engine if a fuel cell gets more miles per kilo?
And you're absolutely right about the system efficiency, at least on paper. A fuel cell system, a good one, might give you 50 to 55% efficiency, whereas a hydrogen engine has historically been lower than that. But in engineering strategy, and especially in business strategy, efficiency is just one variable in a much bigger equation. The total cost of ownership, TCO. And this is where we're now seeing what we call the golden cross.
The golden cross. Okay, explain that. Is that a finance term?
It is, but we've co-opted it for engineering economics. It's the point where the cost lines on the graph intersect and the long-term winner becomes clear. While the fuel cell might save you a little bit of money on fuel over the, say, 10-year life of the truck, the engine saves you a massive amount of money on capital expenditure right up front.
Massive. How massive are we talking? Are we talking a few percentage points, or is it a game changer?
It's a game changer. The data we're analyzing suggests that a complete H2ICE powertrain system is roughly 31% lower in cost than a comparable fuel cell system.
31%.
Yes. A third of the cost just wiped out instantly before the truck even rolls off the line.
That's incredibly significant. But why? What's driving that cost difference? Is it just that fuel cells use expensive platinum and those, fancy proton exchange membranes?
That's certainly part of it, yes. Platinum is expensive, the membranes are complex to manufacture. But the much bigger factor is something we call industrial inertia, or, to put it more positively, supply chain resilience.
Okay.
Think about what actually goes into an internal combustion engine. An engine block, pistons, a crankshaft, valves, connecting rods.
All just heavy metal, right? Iron and steel, things we're good at making.
Exactly. Forged steel, cast iron. And we as an industry have spent the last 100 years building the most efficient, most robust supply chain in human history to manufacture those exact parts. If you, as a company, choose to build an H2ICE, 90% of your hardware bill of materials is compatible with your existing diesel supply chain.
90%.
90. You don't need to build a new billion-dollar clean room factory in the desert. You don't
Right.
need to retrain your entire workforce to handle delicate electrochemical stacks that can be poisoned by a fingerprint. You use the same casting foundries, the same CNC machining centers, the same assembly lines.
So all that sunk cost from the last century suddenly becomes an asset again, not a liability.
Precisely. If you switch to fuel cells, you are effectively writing off billions of dollars of manufacturing infrastructure. If you switch to H2ICE, you are repurposing it. And that, right there, is why the market CAG, or the compound annual growth rate, is just exploding.
You see these wild numbers.
You do. And depending on which analyst you believe, the growth estimates for the H2ICE sector range from a solid 10% on the conservative side to a staggering 142% in specific high-demand niches, starting really from last year, from 2025. The market value is hitting around $20 to $22 billion this year.
142% growth. That suggests a gold rush, not just a transition. But I want to push back a little on this golden cross idea. Efficiency isn't just a line item on a TCO spreadsheet. It's about range. It's operational.
Sure.
If I'm running a logistics fleet and my new fuel cell truck can go 800 kilometers on a tank, but my H2ICE truck can only go 600 because it burns more fuel, that's a real-world problem. That's an extra fuel stop. That's an operational penalty.
It would be, absolutely, if that efficiency gap were static across all operating conditions.
Yeah.
But it's not. And this brings us right to our strategic segmentation. The question isn't H2ICE or FCEV. The question is, where does H2ICE win?
Right.
You don't use it for a last-mile city delivery van. A battery electric vehicle wins there, hands down. You probably don't use it for a light commuter vehicle. But you look at the heavy-duty side.
Long-haul trucking.
Big rigs. Exactly. You look at the M-MAN HTGX. They just launched a 200-unit run of these trucks. Or you look at the work Cummins is doing with their X15H engine. These are machines designed for high load factors. And here is the critical physics nuance a lot of people miss.
Okay.
A fuel cell is incredibly efficient at low power. If your truck is idling at a stoplight or driving slowly through a city, it's great. Very efficient. But as you push that fuel cell to its maximum power, say, pulling 40 tons up a long mountain grade, its efficiency drops significantly.
Why is that?
It's mostly about thermal management. It generates a massive amount of waste heat, and it's actually very difficult to get rid of that heat. You need huge radiators. The whole system gets less efficient under strain.
Whereas an engine?
An engine loves load. An internal combustion engine is actually at its most efficient when it is working hard in that high torque, medium RPM sweet spot. So in a real-world heavy-duty application on the highway, that efficiency gap between the fuel cell and the engine narrows dramatically. Sometimes it even closes completely. At high loads, they can be neck and neck.
Okay, so on the highway, they're comparable. That's a huge point. Now let's get to that dirty part of your phrase, where heavy meets dirty. What does that mean?
This, for me, is the killer app for H2ICE. This is the segment where it's not just an alternative, it's the only viable choice. We're talking about off-road, non-road mobile machinery, or NRMM.
So construction sites, mines, farms.
Exactly. Look at the case studies from JCB. They make excavators, backhoe loaders. These machines work in literal clouds of dust, thick mud, and they are subject to intense, constant vibration.
And I'm going to guess a fuel cell, which is basically a stack of delicate membranes, doesn't like dust.
It absolutely hates it. A fuel cell needs pristine, almost medical-grade air to function. If you put a fuel cell in the middle of a gravel pit, the filtration system alone would be an engineering nightmare. It would clog constantly. You'd be servicing it every day.
And vibration.
Even worse. Fuel cells are these stacks of hundreds of very thin plates with delicate seals between them. Constant heavy vibration, like you'd get in a mining haul truck, can cause microcracks and seal failures over time. A leak in a fuel cell stack is a catastrophic failure.
But a big, dumb piston engine.
A piston engine eats dusk for breakfast. Well, not literally, but it is incredibly robust. It's a block of cast iron. We've spent a century perfecting how to seal them, how to filter their air. We know they can take a beating for 20,000 hours.
Right.
If you're running a mine in Western Australia, 500 miles from the nearest specialized service center, what do you want powering your equipment? A delicate lab instrument or a block of iron that your mechanic can fix with a big wrench?
I want the iron every time.
Exactly, and that is the TCO reality that goes beyond fuel costs. It's about uptime, durability, and serviceability in harsh environments.
There's one more economic factor here we need to address before we get into the tech. The fuel itself. I keep reading about hydrogen colors and different purity grades. Green hydrogen, blue hydrogen, gray hydrogen.
Ah, yes, the infrastructure split. And this is another massive, massive point in favor of the engine in the current landscape of 2026.
Why? I mean, hydrogen is hydrogen, isn't that H2?
Chemically, yes. But practically for these machines, no. Fuel cells are, to put it bluntly, divas. They are incredibly picky. They require something called ISO 14687 grade D hydrogen.
And that means?
That means 99.999% purity. 5 nines. If there is even a tiny trace of a contaminant like carbon monoxide, we're talking parts per billion, it poisons the platinum catalyst in the fuel cell. It coats the platinum, the electrochemical reaction stops, the stack dies. It's an irreversible failure.
So you need ultra-pure, almost lab-grade gas for a fuel cell truck.
Which is more expensive to produce, more expensive to transport, and harder to find. Now look at the engine. The H2ICE is, let's say, the goat of the energy world. It will eat almost anything.
The goat.
It's not picky. You can feed it industrial byproduct hydrogen that might have some nitrogen impurities, maybe a little moisture, a bit of other stuff mixed in. The engine doesn't care. It burns it all without complaint.
That seems like a monumental logistical advantage.
It's absolutely critical for where we are right now in 2026. We have policies like the EU's AFIR directive promising these grand hydrogen corridors, but the on-the-ground reality is that the high-purity infrastructure is lagging. It's being built, but it's not everywhere.
So your fueling options are limited with a fuel cell.
Very limited. If you have a fleet of engines that can run on lower-grade industrial hydrogen, you have fuel security. You can refuel at an industrial gas plant, not just a certified grade D station. If you have a fleet of fuel cells, you are tethered to the few expensive stations that can provide that 5 nines purity.
Okay, consultant, you've made a very compelling economic case. It's cheaper to build, it's tougher in the field, and it's less picky about what it eats. I get it. But I'm still a bit stuck on the technology itself. You said we aren't retrofitting anymore, but an engine is an engine, right? Pistons go up and down, a spark plug fires. How fundamentally different can it really be?
That is the perfect question, and it brings us right to Section 2, the technical core, the combustion revolution. Because to understand why 2026 is so different, we have to look back at what went wrong in, say, 2021.
Back in the retrofit era, as you call it.
Precisely. Back then, what most engineering teams were doing was taking a standard diesel engine block, maybe a Cummins or a C-Hat, removing the diesel injectors, and then just slapping on a port fuel injection system for the hydrogen. They were basically treating hydrogen like it was gaseous gasoline.
And I'm guessing it didn't work out so well.
It worked, but it was deeply compromised. There were two massive, almost deal-breaking problems. First was the power density issue.
Power density.
Yes, this is just simple physics. Hydrogen is a very, very light gas. It's not dense at all. If you inject it into the intake port, that's what port fuel injection, or PFI, is, it has to mix with all the incoming air before it gets sucked into the cylinder.
Okay, that makes sense.
The problem is volume. To get enough energy into that cylinder to match diesel, you need a surprisingly large volume of hydrogen gas. And that gas takes up space. In a typical PFI setup, the hydrogen gas itself displaces about 30% of the air that would normally fill the cylinder on the intake stroke.
Wait, hold on. So a third of the space that should be for oxygen is now filled with fuel before it even gets in.
Exactly. You're losing 30% of your engine's breathing capacity right off the bat. Less oxygen in the cylinder means you can burn less fuel. Less fuel means less power. So you take this big, powerful 15-liter diesel engine, convert it to hydrogen PFI, and suddenly it has the power output of a 10-liter engine. You've lost all your torque. For a trucker trying to pull a heavy load, that is completely unacceptable.
A non-starter. Okay, that's problem one. What was the second big problem?
Backfire. But not the kind you think of out the tailpipe. We're talking backfire into the intake manifold.
That sounds very bad and very dangerous.
It is. It's a catastrophic failure. In a PFI engine, The entire intake manifold is filled with a perfectly mixed, highly explosive mixture of hydrogen and air, just waiting for the intake valve to open so it can go into the cylinder.
Right.
The problem is, hydrogen is incredibly easy to ignite. It has a very low ignition energy. So if you have a hot spot in the cylinder, a little piece of carbon residue, the edge of an exhaust valve that's still glowing red, it can ignite that mixture while the intake valve is still open.
So the explosion literally travels backwards, up the intake pipe.
Yes. Boom, it blows apart your plastic intake manifold. It destroys your air filters. It's a violent engine-destroying event.
Okay, so that explains why the early prototypes were so problematic.
Yeah.
So how does the 2026 Gen 2 technology, as you call it, fix this?
It's conceptually very simple, but it changes everything. We move the injection point. We completely abandon port fuel injection and move to direct injection, or DI.
Direct injection. So that means we're injecting the hydrogen fuel directly into the combustion chamber itself.
Yes, and this is the crucial part. We do it after the intake valve has already closed.
Ah, I see. Okay, so the sequence is different. The cylinder fills up with 100% pure air first. The valve closes, sealing the chamber. Then we spray in the hydrogen gas.
Precisamente. So number one, we aren't displacing any of that precious intake air. We get our full oxygen charge. In fact, because we can inject the hydrogen at high pressure, we actually supercharge the mixing process inside the cylinder. We immediately recover that 30% power loss from the PFI days.
So power is restored.
More than restored. A modern H2ICE can actually be tuned to produce more power and more torque than the diesel engine it was based on. And number two,
No gas in the intake manifold means.
zero backfire risk.
Yeah.
The intake manifold only ever contains plain, inert air. It's an inherently safe design.
Okay, that's a brilliant solution. It solves the plumbing, the basic architecture. But let's get deeper into the fire itself. I'm looking at this Ricardo analysis in our source stack, and they're talking a lot about air motion. They mention a fundamental shift from swirl to tumble. This sounds like we're talking about gymnastics, not engine design. Why does the air need to tumble?
This is one of the most fascinating and counterintuitive parts of modern H2ICE physics. It all comes down to one thing: flame speed.
Okay.
Diesel fuel, as a liquid spray, actually burns relatively slowly, and it needs time to find oxygen. So when you inject diesel, you want the air in the cylinder to spin around the cylinder's vertical axis, like a tornado or a vortex that swirl. That spinning motion helps the slow-burning diesel droplets find fresh air to mix with.
Okay, so diesel likes a tornado. Adam.
But hydrogen is a completely different animal. It's a
Fine.
sprinter. Its laminar flame speed is 7 to 8 times faster than gasoline. When you light it, it doesn't just burn, it wants to explode instantly.
So a tornado is bad for that.
It's terrible. If you use swirl with hydrogen, the flame front gets flung outwards towards the cylinder walls way too fast. It traps heat near the walls, it creates hot spots, which can lead to NOx, and it's just a very inefficient, uncontrolled burn.
So you don't want a tornado. What do you want instead?
No. You want tumble. Tumble is rotation around a horizontal axis. Imagine the air coming in and doing somersaults from the roof of the cylinder down towards the piston and then back up again. A big vertical rolling motion.
Why is that better for a fast-burning fuel like hydrogen?
Because of what happens at the end of the compression stroke.
Yeah.
As the piston comes flying up, it crushes that big tumbling loop of air. Right at the moment of ignition, just before the spark fires, that organized tumbling motion breaks down into organized chaos, what combustion engineers call high turbulent kinetic energy, or TKE.
And chaos is good here.
In this specific moment, yes. That intense, small-scale turbulence rips the initial flame kernel from the spark plug apart, spreading the fire instantly and evenly throughout the entire combustion chamber all at once without letting it hit the walls too early. It's a much faster, more complete, and more efficient burn.
So to get the special tumble motion, you can't just use a diesel cylinder head. You have to redesign the whole thing.
Completely. And that is the absolute core of our no retrofits recommendation. To generate tumble, you need a pent roof combustion chamber design. It looks like the roof of a house, two sloped sides meeting in the middle. The intake ports are angled to create that somersaulting motion. You simply cannot get this kind of performance from a traditional flat-headed diesel engine. You have to design and cast a new head from scratch.
This is really deep engineering. This isn't just a fuel switch anymore. It's a complete fluid dynamics overhaul of the engine's core.
Now, you mentioned high-pressure injection. I want to ask about that. We talked about DI, but in the literature, I also see mentions of HPDI, high-pressure direct injection. What is the difference, and why is there a debate?
Yes. This is what we call the injection war. It's a philosophical split in the industry. On one side, you have standard DI, which you could also call central injection. This typically runs at about 30 to 50 bar of pressure. It uses a spark plug to ignite the mixture. This is what most manufacturers like Cummins and Evian are doing. It's simpler, it's cheaper, it's robust.
Okay, that's one camp. What about HPDI?
This is the route being pioneered by Volvo and Westport, and it is a completely different beast. It runs at insane pressures, 300 bar or even more. And here is the real kicker. It doesn't use a spark plug.
No spark plug. How does it ignite the hydrogen then? I thought diesel used compression ignition, but hydrogen won't auto-ignite under compression like diesel does, right? It's much more stable. You are exactly right. Hydrogen has a very high auto-ignition temperature, so you can't just squeeze it until it explodes. So HPDI systems use a clever trick. A pilot fuel.
A pilot fuel.
Yes. They have a special dual-channel injector. It first injects a tiny microdrop of diesel fuel, just a few milligrams. The heat and pressure of the compression stroke ignites that little diesel flame, and that tiny fireball becomes the spark plug that ignites the massive blast of high-pressure hydrogen that follows it.
Wow, so it's actually a hybrid fuel system running on both diesel and hydrogen at the same time.
It is, yes, and it's incredibly complex. You need 2 separate fuel tanks, 2 sets of fuel lines, 2 high-pressure pumps, and these very complex dual-channel injectors. But the advantage, and it's a big one, is thermal efficiency. Because it mimics the diesel combustion cycle so perfectly, HPDI currently gets the highest brake thermal efficiency, or BTE, numbers in the industry.
So what kind of numbers are we actually seeing in 2026? What's the BTE benchmark?
Right now, a really good, well-tuned, spark-ignited H2ICE is achieving around 45 to 48% brake thermal efficiency. That already puts it right on par with the very best heavy-duty diesels on the road today. But the roadmap from organizations like the Advanced Propulsion Center in the UK, the LTC, is targeting 60% BTE by 2030 or 2035.
60%. That sounds almost impossible. The laws of thermodynamics usually stop you way before you get to a number like that in a heat engine.
It is incredibly ambitious, no doubt. But with advanced concepts like waste heat recovery, new materials, and these extreme lean burn strategies, it is at least theoretically possible. And you have to understand, if an engine ever hits 60% efficiency, the entire fuel cell argument based on efficiency is dead. The engine would be just as efficient, far cheaper to build, and orders of magnitude tougher.
Extreme lean burn. That phrase is a perfect segue to our next section, because we have to go there. Section 3, the physics of emissions. We have to address the elephant in the room. The biggest criticism you hear, the thing that the skeptics always say is, sure, H2ICE doesn't produce CO2, but it produces a ton of NOx, nitrogen oxides, the main component of smog.
This is probably the most persistent and I would say most frustrating myth in the entire industry, this idea that hydrogen combustion automatically equals high NOx emissions.
But isn't it based on real physics? I mean, the Zeldovich mechanism is a real thing, right?
It is absolutely real. The Zeldovich mechanism states that if you heat up normal air, which is mostly nitrogen and oxygen, to a temperature above roughly 2200 Kelvin, the N2 and O2 molecules break apart and can recombine to form various nitrogen oxides, or NOx. And hydrogen, it's true, burns very hot. So the simple logic goes, hot burn equals lots of NOx.
So if the physics is real, how do you cheat it?
You don't cheat physics. You use a different part of physics to your advantage. You use a strategy called ultra-lean burn. We talked about the term lambda earlier. Lambda 1 is the stoichiometric point, the chemically perfect mix of air and fuel where everything burns. In a modern H2ICE, we run at a lambda of 2.5, sometimes even higher.
Okay, let me make sure I understand that. That means you are forcing 2.5 times more air into the cylinder than you technically need to burn the fuel you injected.
Yes. We are stuffing the cylinder full of excess air, and that extra air, all that ultra nitrogen and oxygen, doesn't participate in the combustion. Instead, it acts as a massive thermal buffer. It absorbs the heat of the combustion reaction.
Like a coolant that's built right into the combustion chamber itself.
That's a perfect way to think about it. And because of all that extra air soaking up the energy, the peak combustion temperature never actually reaches that critical 2200 Kelvin threshold. The Zeldovich mechanism never really gets triggered in the first place. As a result, the raw, untreated NOx coming out of the engine drops to near zero. We're talking single-digit parts per million.
Do we have real-world proof of this? Or is this just a simulation on a computer?
Oh, we have hard, verifiable data. You just have to look at the case study published by JCB in partnership with the University of York. They took one of their hydrogen engines and tested it on a dyno right next to their latest Stage V diesel engine, which is the cleanest diesel they make. And here is the absolutely shocking part of that test.
Go on.
The hydrogen engine didn't even use an SCR system.
SCR. Hang on, that's selective catalytic reduction. That's the complex, heavy box on the side of every modern diesel truck. The AdBlue system, the thing that every trucker complains about because the sensors fail and the fluid freezes in the winter.
That is the one. It's heavy, it's expensive, and it's a massive maintenance headache. JCB found that by running their engine in this ultra-lean mode, they could remove the entire SCR system completely. All they used was a very cheap, very simple passive device called an HSC, a hydrogen slip catalyst, which is just there to clean up any tiny bit of unburnt hydrogen gas.
And the result? What was the NOx reading?
Even without that multi-thousand-dollar SCR system, the hydrogen engine produced 50 times less NOx than the fully treated Stage V diesel engine.
50 times less, with less hardware on the truck.
Correct. And this is so important because it leads to a massive strategic debate for us as consultants and for you as a board. Do we, as an industry, chase absolute zero emissions at any cost, or do we accept what you might call net zero or practically zero?
Play devil's advocate for me here. If I'm a regulator in Brussels or California and I see a tailpipe emitting any NOx at all, even a tiny amount, why shouldn't I ban it? Why shouldn't I just mandate that the SCR be put back on to get from 10 ppm down to 1 ppm?
Because of the holistic environmental cost.
Yeah.
You have to look beyond just the tailpipe. Think about what an SCR system is. You have to mine platinum and rhodium for the catalyst itself. Then you have to manufacture the AdBlue fluid, which is urea. Do you know how industrial urea is made?
Some kind of industrial chemistry, I assume.
It's made using the Haber-Bosch process, usually with natural gas as a feedstock. The production of the very fluid that cleans the truck's exhaust actually creates a significant amount of CO2 at the factory. So the expert recommendation we are making is this. If the engine is already 99% cleaner than the diesel it replaces, adding a heavy, expensive CO2-intensive SCR system just to scrub that final 1% is actually a net negative for the planet.
So the cleaner strategy is actually the simpler and cheaper strategy. Just skip the SCR.
For off-road and many non-urban environments, absolutely. We strongly recommend the HSC-only emission strategy. It dramatically lowers vehicle cost, it reduces complexity and improves reliability, and it is, from a total life cycle perspective, good enough for the atmosphere.
That is a bold recommendation to take to a board, but the data seems to support it.
Yeah.
Okay, there's one more emission we need to talk about, though. Particulate matter. Soot. I was always told that hydrogen has no carbon, so you can't make soot. You can't make what you don't have.
And that is 100% true. You cannot make soot from the fuel, but you can make it from the oil.
Ah, of course, the engine lubrication.
Exactly. Inside any engine, the piston rings have to slide up and down against the cylinder wall thousands of times a minute. To prevent them from seizing, they leave a microscopic film of oil on the cylinder liner. When that incredibly fast, very hot hydrogen flame front expands and hits the relatively cool cylinder wall, it quenches, it cools down rapidly, but in that split second, it can partially burn that oil film.
And burnt oil equals ash and particulates.
Exactly. You get tiny amounts of ash and particulate matter. It's what the industry is calling the PM surprise. It caught some early researchers off guard.
Is it a deal breaker? Does it put us back into needing a diesel particulate filter?
No, not at all, but it does require a fundamental change in the lubrication chemistry. We can't just pour standard 15W40 diesel oil into these engines and expect it to work. We need specialized low SAPS oils.
Low SAPS, what does that stand for?
Sulfated ash, phosphorus, and sulfur. We need to formulate engine oils that simply don't produce ash when they are burned. We're seeing lubricant companies like Afton Chemical developing very specific additive packages. They have one called High-Tech 12582 that are specifically designed to resist this hydrogen flame burn-off and manage any ash that is created. It's a whole new field of tribology.
So let me recap. We've re-engineered the cylinder head, we've re-engineered the injection system, and now we re-engineered the oil. This really is a complete ecosystem shift, isn't it?
It absolutely is. And that brings us perfectly to the really tough challenges, the durability problems. Section 4, engineering challenges and material science. Because even if you get the combustion perfect and the emissions clean, the metal itself might not survive the fuel.
And the first one on the list is always hydrogen embrittlement. It just sounds nasty, like a disease for metal.
That's a very good way to describe it. It effectively is a disease for steel. Hydrogen is the smallest molecule in the entire universe. It is so tiny that under high pressure and temperature, it can do something incredible. It can diffuse into the solid atomic lattice of the steel itself.
You're saying it literally squeezes between the individual iron atoms?
Yes. It worms its way into the crystal grain boundaries, and once it's in there, it disrupts the metallic bonds, it reduces the ductility of the metal. In simple terms, it makes strong, tough steel become brittle.
So what happens in the real world?
Catastrophic brittle failure. And when we say catastrophic, we mean it. Imagine a fuel injector needle or common rail pressurized to 300 or even 700 bar. If that steel becomes brittle from hydrogen exposure, it doesn't bend or leak when it fails. It shatters. It snaps like a piece of glass.
I would destroy the engine instantly.
It destroys the engine, and it poses a massive safety hazard. You cannot have high-pressure fuel system components failing like that.
So what's the solution? Do we have to make engines out of something other than steel?
Not entirely, but we have to be very selective about the alloys we use. We have to move away from standard steels to high-grade austenitic stainless steels things with high nickel content, like 316L. The crystal structure of austenitic steel is a face-centered cubic lattice, which is much tighter and more resistant to hydrogen diffusion.
Is that alone enough for the high-stress parts?
For the tanks and the low-pressure lines, usually yes. But for the really high-risk zones, the injector needles, the valve seats, the high-pressure rails, we need more. We need specialized coatings. We're seeing a lot of research into physical vapor deposition, PVD coatings, or advanced aluminum-based nanoceramics like aluminum oxide. These create a completely hermetic seal at the microscopic level, a barrier that the tiny hydrogen molecules just can't get through.
So we're literally armor plating the inside of the engine components against the fuel itself.
We absolutely have to. And it's not just embrittlement. We also have to deal with friction and wear, the whole field of tribology.
Right, because as you said, hydrogen is a dry gas.
Exactly. Diesel is an oil. It's naturally slippery. As it flows through the fuel pump and the injectors, it lubricates everything it touches. Hydrogen provides zero lubrication. It's the opposite. It can actually clean lubricating films away. If you use standard hardened steel valve seats from a diesel engine, you get a failure mode called dry wear. The metal literally grinds itself into dust in just a few thousand miles.
So how do you solve that? Do you need self-lubricating metal?
That is effectively what we're creating. We use a technology called powder metallurgy, or PM, to make the valve seats. We can sinter the metal powder and impregnate it with solid lubricants like manganese sulfide. Or, even cooler, we can leave microscopic pores in the sintered metal and then fill those pores with oil under pressure. It's like a sponge made of steel that slowly sweats oil whenever it gets hot.
That is incredibly cool. That sounds like science fiction. Okay, one last engineering headache before we move to the global landscape, the mayonnaise problem. I saw a slide on this from IAV that looked pretty gross.
Ah, yes, the water problem. We celebrated the fact that hydrogen combustion produces water vapor. It's clean. But that water can also be a nightmare inside the engine.
It's just steam, right?
It's mostly steam that goes out the exhaust pipe, yes. But some of that hot steam, under combustion pressure, inevitably blows past the piston rings and gets into the crankcase, the engine block where all the oil lives.
Okay.
When hot water vapor mixes with engine oil and then gets churned up by a crankshaft spinning at 2,000 RPM, it emulsifies. It turns into this thick, white, gooey sludge.
Which looks exactly like mayonnaise.
And unfortunately, it acts more like glue. It clogs oil filters, it blocks narrow oil passages, it stops lubricating the bearings, and it can kill an engine very quickly.
How do you prevent that from happening?
You need a very aggressive, very well-designed active crankcase ventilation system, or CCV. It's not enough to just let the pressure vent. You need a system that actively pumps fresh, dry air through the crankcase to constantly sweep that moisture out before it can condense and mix with the oil. You also have to manage the oil temperature very carefully, keeping it hot enough to boil off any water that does get in. It's a complex thermal management challenge.
Wow. Okay, so we have covered the machine in incredible detail. Now let's cover the map. Section 5, the regional landscape and competitive analysis. Because this technology doesn't happen in a vacuum. It happens in specific economies with specific policies. Who is winning this H2ICE race in 2026?
It's a really fascinating three-way, maybe four-way split. You have Europe, China, and North America all taking very different approaches, with Japan sort of playing a wildcard role.
Let's start with Europe. Based on the names we've mentioned, like Ricardo and JCB, they seem to be the innovation hub.
I think that's fair. Europe has the deep engineering brains trust. The big consultancies, Ricardo, IAV, AVL, they're mostly based in Europe. And the big players in off-road, like JCB, are leading the charge there. But the real number one driver in Europe is policy, specifically the Euro 7 emission standard.
Euro 7. The big, scary new regulation.
It is. But the crucial battle, which was fought over the last couple of years, was over the official definition of a zero-emission vehicle, or ZEV. For a long time, the EU was adamant that only pure tailpipe zero counted. That meant only battery EVs or fuel cell vehicles.
Which would have killed H2ICE before it started.
It would have, but the industry lobbied hard with good data, and the definition was adjusted. Now, an engine emitting less than 1 gram of CO2 per kilowatt hour is also classified as a ZEV.
And since H2ICE emits no CO2 from the fuel, that 1 gram rule is the loophole that legalized it.
It's not a loophole, it's a lifeline. It was a pragmatic decision. It unlocked subsidies. It allowed H2ICE trucks to enter urban low-emission zones. You combine that with huge funding programs like the Clean Hydrogen JU, which is funding these hydrogen valleys, local clusters of hydrogen production and use, and you can see that Europe is really setting the standard for the technology itself.
But are they setting the standard for scale? For mass production?
No, I don't think so. That title right now belongs to China. China is the scale master.
What makes their approach so different?
2 things: speed and volume. If you just look at the raw numbers of patent filings and academic papers on H2ICE over the last 3 years, China is dominating. Companies like Weichai and FAW are moving at a speed that is frightening to Western companies. Weichai just recently announced they demonstrated a hydrogen engine with over 50% brake thermal efficiency. That's a world-class, record-breaking achievement.
And what about the government support there?
It's massive, and it's multi-layered. At the top, you have the national dual carbon goals. But then you have to look at the really granular policy. There's a standard called GB 36980.1.
That sounds incredibly bureaucratic.
It is, but it's incredibly powerful. It sets mandatory energy efficiency limits for heavy vehicles. It forces manufacturers to innovate or they can't sell their products. And then you have the provincial subsidies, which are even more aggressive. Look at Shaanxi province, for example. They aren't just subsidizing the purchase price of new hydrogen trucks. They are waiving all highway tolls for them.
Wait, waiving the tolls completely? For a logistics company, tolls are a massive operating expense. That's pure profit going right to their bottom line.
Exactly. That is how you force a market into existence overnight. You make it significantly cheaper to run the clean truck than the dirty one.
Okay, that's a powerful strategy. What's happening in North America?
North America is, as usual, taking a more market-driven, pragmatic approach. The big regulatory driver is the upcoming EPA 2027 standard, which is tightening NOx limits again. But the market response has been led by one company in particular, Cummins.
Right.
Cummins is the king there. And their strategy is brilliant. They have developed what they call the fuel-agnostic platform, specifically the X15H.
I've seen this. It looks like a Lego set for giant engines.
That's a great way to put it. It's a brilliant manufacturing strategy. They've designed and built one universal engine block, the whole bottom half of the engine, that is the same for every fuel. Then, depending on what the customer wants, they bolt on a different head and fuel system, a diesel head, a natural gas head, or a hydrogen head.
So they get these massive economies of scale because 80% of the engine parts are the same, regardless of what fuel it burns.
Exactly. It dramatically lowers the cost of entry for H2ICE, and it gives their customers flexibility. It's a very smart, very American approach to the problem.
And finally, Japan. You call them the wild card. Why is that?
Because Japan, and specifically Toyota, is playing the long game. They have this famous multi-pathway strategy. They refuse to go all in on batteries. But what I find most interesting is their testing ground, motorsport.
The Super Taikyu Endurance Racing Series.
Yes. For the last few years, they have been racing a Corolla powered by a hydrogen combustion engine, first with gaseous hydrogen and now with liquid hydrogen. And they are breaking things constantly and very publicly.
Why is that a good thing? Why is failure good?
Because it teaches you things faster than success ever will.
Yep.
In one race, they had a catastrophic failure of their cryogenic liquid hydrogen pump. The pump has to move liquid hydrogen at minus 253 degrees Celsius while spinning at thousands of RPM. The bearings seized.
I mean, that sounds like a nearly impossible engineering challenge to begin with.
It is. But they diagnosed the failure, they redesigned the bearings, they changed the material tolerances, and they were back on the track for the next race. That data, that specific hard-won knowledge of how to make a cryogenic pump survive under G-force and vibration, is now proprietary Toyota knowledge. No truck company in the world has that data. Toyota does. That gives them a potential 5-year lead on the durability of future liquid H2 systems.
That's a fascinating insight. Which brings us perfectly to our final section, Section 6, Strategic Recommendations. So, consultant, we are back in the boardroom. The client is waiting patiently. Based on everything we've discussed, the TCO, the physics, the metallurgy, the geopolitics, what is the clear, actionable roadmap for 2026 to 2030? What do we tell them to do right now?
Okay, for the board, we have 4 key high-level recommendations. Recommendation number 1, and it's the most important, stop retrofitting immediately.
Be blunt with them.
We have to be. Do not take your existing inventory of diesel cylinder heads and try to convert them. It is a technical and a commercial dead end. You will suffer from power loss, you will risk backfires, and you will lose to the competition who are building dedicated engines. You must invest, starting today, in a dedicated Gen 2 architecture. That means pent roof heads, high tumble intake ports, and a 350-bar direct injection fuel system. If you are not designing your engine specifically for hydrogen's unique flame speed, you are not really in the game.
Crystal clear. What's recommendation 2?
Go digital. We just spent a lot of time talking about tumble and turbulent kinetic energy and fuel mixing. These are incredibly complex fluid dynamics that happen in microseconds inside a sealed metal box. You cannot effectively tune this by trial and error on a dynamometer. You will melt pistons and waste millions of dollars before you find the right calibration.
So simulation is key.
It's not just key, it's mandatory. Digital twins. You need to be using advanced CFD software packages like GT Power, Converge, Wave. You need to build a virtual model of your engine and simulate the combustion thousands of times before you ever cut a piece of metal. If your current engineering team isn't fluent in high-fidelity CFD, you need to hire new engineers who are.
A strong directive. What's recommendation 3?
Rationalize emissions. This is probably the most controversial one for the lawyers and the policy people in the room. You need to push back strategically against the tailpipe zero dogma.
You're telling the board to go out and lobby the regulators.
I'm telling the board to embrace the science and the data, specifically to embrace the HSC-only strategy for all of your off-highway products. Do not put a complex SCR system on an excavator or a mining truck if the regulation doesn't explicitly force you to. The added cost, weight, and complexity will destroy your TCO advantage over diesel. Be prepared to argue that accepting 10 ppm of no-NOx is a better holistic outcome for the planet than adding a system that costs 30% more and has its own carbon footprint. The environmental math supports you.
And the final recommendation.
Safety first, and specifically component-level testing. The big safety regulation for hydrogen vehicles is ECE R134, and it is brutal. We have seen multiple companies build a beautiful, functional prototype truck, only to realize at the very end that the way they mounted the hydrogen tanks is 2 inches too close to the edge of the frame. They fail the crash safety certification.
And then they have to go back and redesign the entire chassis.
Yeah.
A disaster.
A year-long, multi-million-dollar disaster. Exactly. Or they find out that the O-rings they chose for their fuel fittings are getting brittle and starting to leak after 6 months of real-world vibration. Do not wait for full vehicle integration. Test the components now. Test the materials for embrittlement. Test the tanks for drop impact and bonfire scenarios. Fail early. Fail cheap on a test bench, not late and expensive on the road.
That is an exceptionally clear roadmap. A dedicated architecture, heavy reliance on digital simulation, a pragmatic approach to emissions, and rigorous early component testing.
That is the playbook. That is how you win in the H2ICE space in 2026.
So let's wrap all this up with one final thought for our board. We started this deep dive by talking about the supposed death of the internal combustion engine. But we spent the last hour providing evidence that for the heavy, dirty, essential jobs that keep civilization running, the engine is actually technically superior.
It's not a bridge technology to get us to fuel cells. For these applications, it is the destination.
And I think that's the real aha moment here. For years, we've all been looking for some magical revolution in battery chemistry. We've been waiting for a miracle that makes fuel cells cheap and indestructible. But maybe the revolution was sitting right in front of us the whole time. It just needed a new kind of fuel.
We are simply pivoting 100 years of accumulated combustion know-how. We are taking arguably the most reliable, best understood machine in human history, and we're making it clean.
When you put it like that, if an engine emits nothing but harmless water vapor, can run for 1,000,000 miles, can handle the dust and grime of a mine, and costs about the same as a diesel to build, why are we still debating if the internal combustion engine is dead? Perhaps it hasn't died at all. Maybe it's just been reborn.
A rebirth of fire, fueled by hydrogen.
I love that. A rebirth of fire. That is a wrap on our deep dive into the 2026 Global H2ICE technology strategy. To our board of directors listening in, thank you for hiring us. We hope our report was worth the consulting fee.
Download the white paper in your mind, and it's time to rethink your fleet strategy.
Thanks for listening. We'll see you on the next deep dive.
Goodbye for now.